Hey everyone, welcome to the last lesson of Unit 7. I saved the best for last. We're going to be doing some graphing of radical functions today. Yesterday we looked at a problem where we had to do some graphing with a radical and it made a huge table. If you want to be reminded of the horrors that it was, it looked like this. But today what I'm going to do is show you how to graph radical functions in a way that's a little bit nicer and just you don't have to worry about a table by the end of this. And so just trust me, it's going to be okay. So graphing a radical function, we're going to use translations, and some of this should look pretty familiar. We've got this letter A in front, and that tells us what our vertical stretch is going to be. It tells us how much is our graph going to get like taller and how much is it going to get shrunk down. That didn't really work to use my hands, but that's okay. We're going to look at horizontal translation. So anything that's under the radical that's added or subtracted, we move it means we move the graph left or right, but it's always opposite of this sign. Does that sound familiar? Maybe. Anything that's outside is a vertical translation, up or down, but the sign stays the same. But before we actually dive right into that, let's look at some parent functions. This is going to be very important. We have this function. So if I have the graph y equals square root of x, yesterday I talked about wanting to graph perfect square numbers. And so perfect square numbers would look like this: 0, 1, 4, 9, 16. I'm not going to go beyond that. But if I plug in 0, I get 0. The square root of 0 is 0. If I plug in 1, the square root of 1 is 1. And then things get a little weird. The square root of 4 is 2. The square root of 9 is 3. And my graph is going to look like this. It's something that's going to kind of look like half of a sideways parabola. That's the best way to describe it. And yesterday I told you guys why we couldn't put an arrow on the other end or extend this going this way. What was the reason for that? The reason was because if I plug in -1, I actually get an imaginary number. There's no imaginary numbers to graph over here. It's just real numbers. So I can't plug in a negative number. So that is the parent function of a square root. But let's look at the parent function of a cube root. So what would the first 4 perfect cube numbers be, starting with 0? It'd be 0, 1, and then I've got 2 cubed, which is 8, and 3 cubed, which is 27. So obviously I'm not going to be able to graph 27. But remember that with cube roots, I can graph negatives on this. I can take the -1, I can take the cube root, of -1 and of -8, -27, and I can get real numbers. So when I take the cube root of -8, I'm not going to try to graph -27. Cube root of -8, I get -2. Cube root of -1 is -1. Cube root of 0 is 0. Cube root of 1 is 1. And cube root of 8 is 2. And it makes this, I think, kind of satisfying little S-curve thing here. But you all know how I feel about graphs. I love them. They just are so nice. Look at that. Isn't that gorgeous? Some of you are shaking your head at me, and that's okay. So we need these parent functions if we're going to do any sort of translating. So coming down here, we've got graph the function square root of x minus 3. So let's first start by identifying our translation. Our translation, I have one number there, and it's a -3. It's outside. So what am I going to do for a translation with this? It's going to go down 3. So what I'm going to do is put my parent function of the square root function on here. And you guys are going to do this enough that you start to memorize 0, 0, 1, 1, 4, 2, 9, 3. You don't have to make a table for this every time, or you shouldn't have to make a table. And I'm just going to do a dotted line to show that it's not my final answer, but it's part of my work. And then my translation says to move everything down 3. So I'm just going to take each point and move it down 3 units. 1, 2, 3. There we go. And then I'm going to connect them. That's the only translation in this problem. So that is my final answer. That's it. All right. Let's graph this one. What kind of translation is going to happen here? Because that -1 is inside, we're going to move to the right 1. Remember, if it's inside the or under the radical, we do the opposite operation. So putting my parent function on here. I'm going to take each point and I'm going to move it to the right 1. They're going to be a little close, but that's okay. That's it. That's all we're doing. No tables necessary. All right. So this one's a little bit complicateder. This one's going to require a couple of steps because we have this -3 in front. So I'm going to still start by drawing my parent function. 0, 0, 1, 1, 4, 2, and 9, 3. Oops. Clean that up a little, sorry. Okay. And now, because there's that -3 there, before I do any translation, what I'm going to do is take each of my y coordinates and multiply them by -3. This means stretch this by a factor of -3. So if I do 0 times -3, it's just 0. Let me make a note here. If I do 1 times -3, I get -3. If I do 2 times -3, I get -6. And if I do 3 times -3, I get -9. So my graph, I'm still going to use dotted because it's not the final answer. Notice a couple of things happened. One, this graph grew. So it went from, kind of being this nice normal little guy to being like super tall. The other thing that happened was that it reflected across the x-axis. That's because this is a negative. When this is a negative, just like we've seen before, that negative reflects it across the x-axis. If this had been a 1/2, what do you think would have happened to the shape of the graph? Instead of getting taller, it would have gotten shorter, or it would have like gotten smushed down. So thinking about like with parabolas, same thing happened when we had, similar thing happened. The one, if it was less than 1, it had one effect, and if it was greater than 1, it had another effect. So we have taken care of that. Now we can do our translation. So what translation is happening here? This is moving right 2 and down 4. So each point of my new, this was my, let me number these actually, sometimes that helps. This was my first graph. This is my second. Each point of my second graph is going to move to the right 2 and then down 4. So I'm going to take this one and move right 2, down 4, right 2, 4, 1, 2, 2, 3, 4. And I can't fit the other one on the graph, and so that's okay. I'll just kind of give the best shape there. That is about as complicated of a problem as you are going to get. Okay? Whew. Let us look at some cube roots. Oh no, not yet. Sorry, one more square root. So explain to me what you know about the shape of this. What's going to happen? What are some things that are going to happen? Well, one thing that's going to happen is it's going to shrink. I'm going to multiply each y by 1/2 and it's going to shrink it. The other thing that's going to happen is that we are going to move everything left 2 and up 5. Okay, I'm going to go through this one pretty quickly. I've got my parent function. I guess you don't technically have to draw the dotted lines, but it just helps me. Multiplying by 1/2. Ooh, this is going to be tricky. Looks like this. Okay, and then left 2 up 5. So I'm going to move left 2 up 5. This one would go left 2 up 5. So at that 5.5. This one would go 2, 3, 4, 5. 1, 2, 3. It's kind of tricky moving things that have fractions because I want to make sure that I am keeping that in between, like at the halfway mark. So this one ended up moving to 6.5. Just be careful that you're not moving it to a whole number. And this would be my final answer. Notice that it is a little bit shorter than the other one. All right. Cube root. Let's take a look at this. I see a negative in front. The negative in front tells me that it's not going to stretch or shrink, but it is going to be reflected from the parent function. I see that I'm going to move everything left 1 and up 3. All right, so let's dive right in. My parent function with cube roots looks like this: -8, -2, -1, -1, 0, 0, 1, 1, and 8, 2. And actually, when it's a coefficient of -1, when it's an a value of -1, that's kind of my favorite because it makes this super awesome looking shape. It doesn't take a lot for me though, you know. But come on, tell me that does not look cool. That looks so cool. Okay, and then I'm going to take, so that was my second equation. I'm going to take each of these points and move left 1 up 3. 1, 2, 3. Left 1 up 3. I almost forgot my centers. Left 1 up 3. Left 1 up 3. And there. So when I connect the dots, it looks like that. All right. Yeah, we can do one more. Okay. This one is a little bit easier. There's no stretch or shrink value. So just putting my parent function on here. Like I said, if you're sitting there going, how does she do that so fast? Do this enough and you will have these values memorized. And my only rule is to what? My only rule is that I have to go down 2 or shift down 2. So each point gets moved down 2. And then I connect those dots. And there you go. So that is graphing radical functions. I'm not going to have you graph any fourth or fifth roots. We'll keep it to square and cube roots.